Good afternoon. So let's begin with lecture 9. I want to make sure everything is turned on. Yes, good. So this is the fourth and the last lecture on combinational logic. From next time we will be studying sequential logic, which is also very interesting. Another reminder that the quiz is this Thursday. Is there any other review session scheduled? There is a review session tonight at 7:30. 6:120. Very good. Design trade-offs in arithmetic circuits. So algorithmic trade-offs in hardware design, it's really a very interesting topic. I mean, if you design arithmetic circuits, there is no end to it. Theoreticians get into it and practitioners get into it, and you will get a flavor of why that is the case, why it's so interesting and why it's can be so difficult to get this thing to actually pay off, whatever tricks you have. So I think the reason is that we are trying to, it's a multi-dimensional optimization problem. On one hand, we want to minimize the area taken by your circuit. We also want to minimize the delay, given the input, how soon you will get the output coming out of the circuit. And lastly, but not the least, is power. And we look at power later on in the course, but not right now. Okay, so these trade-offs, the most important thing to remember in this is you have to have a high-level idea of, for example, if you're talking about arithmetic circuits, how to add numbers or how to multiply numbers, because there are many different algorithms for doing that. And in hardware, the trade-offs are different, so some algorithms may do extremely well. In fact, many algorithms have been studied in this primarily because we want to design better hardware, for it. So whatever idea you have, whatever algorithm you have to express it somehow, in some high-level description language, and then you feed it to the compiler, and it produces some code. Well, you would think that's straightforward. The problem is these tools can do so many optimizations that sometimes the results are surprising to you, because you are convinced that algorithm A is better than B, and then when you feed it in the compiler, you don't see much difference, because it's conceivable that the optimizations done by the compiler already took care of what you thought was very efficient, or there was some hidden cost that you didn't see before. So this is another reason why synthesis is extremely important in this case. We need to understand theoretically why we expect A to be better than B, but we also need to see in practice, is A better than B? And I'll give you a flavor of that today. So choosing the right algorithm is the key to design. You cannot compensate for a bad algorithm. I mean, if your design is if your algorithm is not good, then you can't. I mean, this issue is exactly the same in software. That's why algorithms are prime, right? Algorithms are very, very important, regardless of what we do in computer science. But algorithms don't exist in a vacuum. They exist under some cost model. And the hardware cost model is sometimes different than software cost models. And again, that will become clearer in this lecture. So what we are going to look at today is the design of a better adder. This is not just a made-up problem. Later on, when we design sequential circuits and complex things like your RISC-V processors, we worry about how fast we can run it. And you will discover often the adder is the one that is slowing down everything. So, you'll be dealing with it in your project. By that time you'll say, gosh, what I need is a faster adder. I should have paid attention to those early lectures, right? But we can go very, very far without ever worrying about faster adders. But if it is the thing that is slowing down everything, then you will have to pay attention. So in other words, we pay attention to fast adders not just because we want to add fast, but because if we don't add fast enough, the whole machine can slow down. Okay, so you will get a much better feel for that. So let's visit our famous ripple carry adder that you have seen, which you can implement quite easily. And if you try to understand the delay through this, the easiest case to understand is that in the worst case, the carry in, the first bits from the least significant bit have to go all the way to the most significant bit, and it's done one by one. So there is a path of this sort, and this path obviously is the same size as the number of full adders in your design. So if you have 32 full adders, you are adding the delay of 32 full adders in order to get the thing. We can write it more precisely that the propagation delay of this ripple carry adder is going to be n minus 1 propagation delay from C input to C output, because I'm giving carry in, there is a carry out, and it's being chained, right? And at the end we have to, of course, produce the sum bit using the last carry bit, so that's the last number that is added. So we will often use a notation in this class, and you will use it actually in all classes. You have already seen it, but you haven't seen it, then this is your introduction to it. We say this computation is order of n. That's how it's read. This big O(n) is order of n. That means the delay in this circuit is order of n. Right? Order of n tells us that the latency of our adder grows linearly with the number of operands in it. So if you build a 64-bit adder, it's going to be, the delay is going to be of the order of 64 in this case. I mean, it'll just get bigger. Now exactly what is this order of notation which we use quite heavily, and why do we use it? So suppose you did some exact calculation, how much is the delay, and the delay turned out to be n squared plus 2n plus 3. It could be just number of steps in your computation, all right? So whatever you are counting, suppose that number is n squared plus 3n plus 3. So I can think of it in shorthand, because if you look at this number, it's always between 2n squared and n squared, whatever this polynomial evaluates to, except for a few small integers in the beginning, right? So if you forget about 1, 2, and 3, then this number is always going to be between 3n squared and 2n squared. In other words, from our point of view, this computation is of the order of n squared. So that's what the meaning is. We don't have to worry about all these constants. It's tedious, right? But we can remember the orders quite easily. So formally, you will say that some computation is of order of Fn if the following property holds, that Gn always falls between f of n, I mean some constants multiplied at both ends, C2 Fn and C1 Fn. So as long as your computation falls between that, we say it's of the order of Gn, this computation, sorry, order of Fn. Okay, so I say that, but there is always some integers which we may be willing to ignore, right? Some starting points, because they are strange, and we don't care. I mean, we are much more interested in this analysis when we are talking of large n. That's why asymptotic analysis here. This is just a throwaway. If you see, there are two different order of notations. It's called big O and small o. So when you use big O, then both these inequalities are enforced, right? There is a C1 and C2 between which this Gn will fall, sorry, this Fn will fall. On the other hand, when only the lower number matters, you promise that it will not be larger than this, then it's called small on, and that is implies the first. So that's a very subtle difference. But believe me, whatever you get or don't get about this notation, you can't escape from it if you're going to graduate in this department. Every course is going to use it. It's part of common jargon. When we talk to each other, we say, yeah, but that's just, order of n. He says, no, it's log n. No, it's n cubed, whatever. So this is just something you have to get used to exactly what this notation means. So here is my first idea for, yes?
So I'm pretty sure the first is theta, and the second is big O, and little o is like O left.
Sorry, the bigger one is?
With both inequalities, it's theta in.
Right.
And then if it's only the first inequality, then it's big O. Little o is the second inequality.
Okay. All right. So there are many O notations, right? But at least you have to have some sense for exactly what this number means. Okay, so let's start with our adder. What is our problem? Our problem is that the carry goes all the way from the least significant full adder to the most significant one, and we want to break this chain. So here is an idea. Why don't we throw some extra hardware at the problem? So I add 16 numbers, and I add the higher order 16 numbers too. Let's just assume that the carry input is 0. And in the other circuit, I assume that the carry input is 1. Yes, so that's what is shown in this picture. So do you agree that I can, under this assumption, I can add the lower order bits and the higher order bits in parallel? Both those computations are being carried out, even though I don't know the carry that will come out. And then what I can do is I can select when I actually know the carry. So after a while, these lower order 16 bits is going to produce a carry out. And I can use that carry out to select one of the two answers. Why is this a good idea?
Because it makes not every operation sequential, like things can happen simultaneously.
Right, so the worst delay now has gone from 32, right? It has gone to 16 plus change, right? So you have this 16, and a mux. Mux also always introduces a delay, right, of 1 or 2 gate cycles in this, not gate cycles, 1 or 2 gate delays. Everybody sees this? That you will expect the delay in this to be carry out of the low, selects the correct version of the high, whatever we have added in parallel over there. So we have cut down the delay in this, from 32 to now we have to talk about TPD 16 plus TPD of mux, whatever that delay of mux is. And if we use 16-bit triple carry adders, we would roughly half the delay over 32-bit triple carry adder. And what is the price we paid for this?
Area.
Sorry?
Larger area.
Area, because we have more hardware now, right? We have an extra, the 16-bit adder for the high bits, as well as we have a mux. Very good, right? So the drawbacks are obvious, consumes much more area than triple carry adder. Wide mux adds significant delay. So remember, in hardware, muxes are not free. People are always surprised by how much area is taken up by muxes, right? I mean, they take area and they add a few gates of delay also in everything you do. And often, if you have a very wide mux being controlled by one control line, that means this line has to be sent to all the gates, right, which are horizontally laid out for you. So that means this is also a problem, because when you have very huge number of outputs coming out of a gate, then that also consumes a lot of power. That also introduces delay. So we often put more oomph on these lines, when the output is going to be duplicated many, many times. So wide muxes are certainly not free in hardware. Okay, so can you write code for this? It's pretty trivial to write the code for this, and let's see if this makes sense. I can't see it very well from here. So I'm calling Carry-Select Adder 32 bits. So you have 32 bits in, and you have some carry in into this. And then I'm computing the lower order bits using a add 16 adder. So I'm giving the lower order 16 bits and the carry in. And then for the higher order stuff, what I'm doing here is I'm testing if the bit is 0, then I'm feeding a 0 as carry in, and if it is 1, then I'm feeding 1 as the thing. But this is a conditional, is just a way of expressing it. In hardware, it's all happening in parallel. Except for that selection, that final selection cannot happen unless you know the value of CSL16. You have to know that 16th bit that is coming out of that. There are several things I want you to notice about this, right? We could have used any add circuit here, right? We can use any add circuit. In fact, if we want, we could have speeded up this 16-bit adder using the same trick again. You know, break it down into 8 bits and 8 bits. Does everybody see that? Right? We can apply the idea recursively. If we could have speeded up 32-bit adder using 16-bit adders, well, then I can apply the same trick to 16-bit adder and speed it up. Okay, so let's suppose we did that. Suppose we wrote it recursively, you know, in this. So the higher order bit remains the same, and all I did was, instead of calling general add 32, I'm calling carry-select adder of 16 bits. Can you define a carry-select adder for 16 bits? You can define it for 16 bits, you can define it for 8 bits, you can define it for 4 bits, 2 bits. At some stage it becomes a full adder, you know, at the bottom. So I'm not writing down all these definitions, but if you understand the one for 32, you should easily be able to fill out all these functions. So this is a recursive carry-select adder. I'm not saying it's necessarily a good idea, but this is just the point that whatever trick I use to break up the 32-bit adder into 2 parts, I can take the smaller part and break it again, break it again, break it again. Can somebody remind me, why are we doing this? Why are we breaking it into smaller adders? Yes, please.
You're trying to speed up the computation.
Right. Specifically what in the computation?
The amount of time.
No, I know, but what signal was slowing us down here?
The ripple.
The rippling of the carry signal, right? So carry signal is the problem, right? Because it starts here and it ripples through the thing. And what we have done by playing this trick is, in the first stage, we cut down the propagation delay by half. In the second stage, if we break down the 16 to 8s, we'll cut it by half again and half again. So how many steps before you will run out of these things to do? Log n steps, right? So instead of having a delay of the order of n, now you're going to have a delay of the order of log n, right? This is a very standard kind of a trick, and you can program this. And indeed, you will see, you know, there is a dramatic improvement in delay, hopefully, right? Because I don't trust results until we see them synthesized. But let's try to guess the area. How much area is being taken up? Does this calculation make sense to you? How much area is taken by carry-select adder 32? So you had one 16-bit and 2 more 16-bit adders, right? So I have written here 3 carry-select adders of size 16, plus how big a mux? You know, I have 16 bits plus carry, you know, so 17 bits have to be mux because I have to select finally between them. All right. And then if you keep substituting at 16, similarly you can see it's 3 of correct select adders of size 8 plus a mux of size 9. And if you keep going down, 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 here, you know, ultimately you get down to full adders. which roughly are 5 gates in this, and a mux is roughly 3 AND gates. Remember the mux, right? We had 2 ANDs and an OR, you know, the output of it, so that's 3 gates. If you add it all up, how many gates? I didn't add it up, I just typed it in Google. It told me 2339 gates. Is that a lot of gates? How many gates in your ripple carry adder? You had 32 full adders, right? And if you assume that it's 5 gates per full adder, then it turns out to be 160 gates. Whoa! We went from 168 gates to 2339. Why? Because we believe that the delay of the circuit is better, because it will propagate the carry faster, but it's much bigger circuit. Now what you will discover is there is a lot of duplication going on in this circuit, this recursive carry-save adder. There are lots of things which can be shared actually across. Whether you do it or not, the compiler is going to do it. So the actual gate count may turn out to be much smaller than 2339. Okay, I can write it differently so that it will be, some of it will be obvious, but you just, you know, why do the work if the later on tools are going to do the work, you know, for you? But you need some tool to know exactly how much area it will take. So I'll show you some results at the end of the lecture after we have discussed several different adders and see what is the actual area and delay of these things. Do people get the idea of a recursive carry-save adder? If you understand the trick at the highest level, all I'm doing is I'm applying the trick repeatedly. And it's really not very difficult to write these codes in BlueSpec, but of course you need some practice to do that. Let's re-examine the problem again, right? So I'm going to a new class of adders which look different, you know, so they are called Carry-Lookahead adders, CLAs. And there are many of them actually, but they all share a general idea. So this is my picture of full adders, and the culprit was that the carry in begins and it ripples through, right? If we do it in a naive way. So suppose by magic, by some huge cleverness, I could generate all the carries very fast, right? Suppose I could generate all the carries in much shorter time than order of n. So I'm going to put some extra circuitry over there, right? Feed the same things, A, B, and carry in. But my goal now is to produce these 32 carries that are coming out faster than order of n. Perhaps I can do it in log n. Why? Because you have already seen there is some solution out there which can do this addition in log n. So that's what Carry-Lookahead adders are all about. Clever ways of generating this carry signals. We'll ignore the sum bit for now, right? And we'll just focus on the top half of this picture. Let's see how fast we can generate all these carries. Okay, key idea, transform the chain of carry computations into a tree. And this transformation is very well known. I mean, if I gave you the problem of adding n numbers, right? One way will be you add it here, you add it here, you add it here, right? So you're doing all the additions in sequence. Another idea will be that you add these two and these two. This can be done in parallel. And then you add these two. So the moment you do that, instead of linear time for adding the numbers, the time will become proportional to the depth of the tree. Log n is the time. And this trick works on almost any associative operator. Right? So as long as your operator allows you to, combine it with left or right, you can do this tree fashion thing. It's a very standard trick. You will use it over and over again, both in hardware and software. But the carry look-ahead problem is slightly trickier than that. But we are drawing some inspiration from this. Okay, let's begin with the full adder again. Right? So this is the table for the full adder. And I can write down the Boolean equations. How did I write down these equations? What is the sum bit? Just look at all the entries in the truth table where the sum is 1, right? So I wrote down you should be ready for this. Now a quiz is coming up, right? You can write down Boolean expression for this in a very straightforward way. Right, so it's 1 in 4 places, so you have 4 product terms over there. And now I can optimize it a little bit, right, and get something like this. And, I generate a circuit. So this is why I keep referring to full adder using 5 gates, etc. It's taking 5 gates after optimizations, because if I directly implemented, this full Boolean expression, it will take many more gates. But this is the kind of optimization that is well within reason for compilers to do these days. All right, so let's understand what optimizations are going on so that you have more insight into this. So the sum bit, and what will happen if you take the first and the last term, they both have C in as input. Right, so one case you have C in, the other case you have minus negative of C in. Can somebody tell me what is that computation in the parentheses?
It's an XOR.
It's the exclusive OR, right? A not B plus not B A, sorry, not A, B. So one is exclusive OR, the other is negative of. So you can do it like this. And that again looks like exclusive OR. So when you do this, the sum bits becomes really 2 exclusive ORs. Think about it for a second, that makes sense, right? When do you produce a 1 bit out there? All right, I can do similarly optimizations on the carry bit over there, and in this case also I'm going to take what is in C in. If you look at that computation inside, it's again A exclusive OR with B, and the other one, what happens? AB is getting, in the last 2 terms, AB comes out and you have C in plus not C in, which is same as 1. So this optimized to this. I'm just repeating this, right? You have seen this before, but I want you to be very comfortable with this. This is the kind of thing I expect you to be able to do in your head, but if you forget it, compiler will do it for you, most likely. Okay, so now we have that other optimization which is called sharing common sub-expressions. So I see that A exclusive OR with B is being used twice. So I can say T is A exclusive OR with B, and sum is T exclusive OR with this, and C out is T dot in plus A dot B. So this is how that formula was derived. There is a reason why I am spending so much time on full adder. Because all the insights for Carry-Lookahead adder actually come from full adder. What can we do? How can I combine it so that I can propagate the carries faster in it. This is just an aside that, if instead of using exclusive OR here, I had used A plus B, that is also correct. You can verify that drawing the Boolean picture for it. Okay. Now comes the next idea which you have to understand carry-lookahead adders. And that is the idea of generation of a carry and propagation of a carry. So now I'm focusing simply on the carry signal, right? So if you see what is in a carry signal, it's A dot B, and the other part is something, A exclusive with B dot C in. What do you think of A dot B? What does it tell you? If you just read this Boolean formula, this says this full adder is going to generate a carry if both A and B happen to be 1, regardless of what Cn you have. Right? So we call it generates a carry. And what about the other thing? If that turned out to be 1, then if the carry in is 1, then the carry out will be 1. Hence we call it propagate. This factoring is being done very carefully. Alright, you will see why I'm looking at it like that, but first let's just get used to the names. So I could have written it like this: carry out is generate plus propagate dot C in. Are you comfortable with that formalism? That Boolean formula, right? You're saying under some conditions this just generates a carry. And in some other cases it propagates Cn. One step. So there are two ways carries come out of this system. Okay. Now just to reinforce again, why do I call it generate? If G is 1, then C out is guaranteed to be 1, regardless of what C in is. And if P is 1, okay, if P is 1, then C out is going to be the same as Cn in this case. Propagate, right? Generate and propagate. This is the most important thing to notice. The G signal and the P signal do not make use of the carry bit. It's giving you some hint. It's giving you some hint that maybe I can take a big thing and figure out the property of whether it's going to generate a bit, carry bit, or whether it's going to propagate a carry bit. I may be able to compute this without knowing the carry in, if I can figure out how to compose these things. Should I repeat myself? Right? That when you look at an adder, either it generates a carry, which means it doesn't care what Cn came in, or it propagates a carry, which means it will produce a 1 provided the carry in is 1. Generate and propagate, these are the two properties. Generate and propagate properties do not depend on the value of Cn. Therefore, there is a chance that maybe I can compose it, so that I can take a 16-bit quantity, 32-bit quantity and figure out, what is its generative property, what is its propagation property. If we can do that, then in the end we'll be able to figure out, how to propagate the carry in very fast, from this. Okay, so let's see how this composition works. All of you understand this picture, right? Ripple carry adder. All right, so let me just express it in terms of generates and propagates. So do you agree that the carry of the high bit here is either the high part generates a carry, GH, sorry, why G, okay, generates, what am I doing, okay, generate, or it propagates, right, so it has E of I, and that matters only if CL coming in is 1. It seems I'm repeating myself, right? But let's do a substitution in this. All right, so what do you know about carry low? What does it depend upon? Carry low depends upon the generative property of the low circuit plus the propagation property of the low circuit. All I did was simple algebraic substitution for CL, and now I can look at this and simplify it further. Are any light bulbs going up, when you look at this? So if I look at these two boxes, these two full adders, which you can in general think of as high, low, right? Because idea is going to generalize to n bits very soon. In this, what you'll see is you can figure out if this is going to generate a carry. So I've given you a composition. I've given you a high bit, low bit adder, and if you tell me properties of these two adders, I can tell you under what condition the whole thing will generate a carry. And similarly, I'm telling you under what condition it will propagate the incoming carry. If it turns out that the propagate of high is H and the propagate of low is PL, right? So if I just if both of them can propagate, then whatever comes in will go out. And if you look at it like this, now I can draw it differently. I'm saying let's not worry about C in for a second, right? You have these full adders, and I'm just calling them full adders, but really you can see that given A and B, I can compute the propagate and generate bits for them. So that's what I did. I'm showing you GH-PH. I'm showing you GL-PL in that. And then I have just, by the algebra on the left-hand side, showed you how to combine these two things, and that is what this capital GP is. This is my composition box. It takes the G and P signals from the high side, it takes G and P signals from the low side, and it produces the G and P signal for the whole thing. That's what we were after. What we wanted somehow was to be able to propagate without touching C in. Right? So we are not home yet, but at least what I have shown you, it's possible to figure out the propagate and generate properties of these very large networks, right, without knowing C in, because that property only depends on A and B, which I can all compute. And now, and this is the composition that GP does over here. Let's put it all together. All right. So this is the box I was drawing as full adder. I'm just going to call it a green box. So do you agree with me that if I give you A and B, you can compute the G and the P signals? And I'm just being lazy here, so I don't want to draw so many wires. And you guys are now world champions in understanding data structure, so that wire is actually a G signal and a P signal coming out. Everybody is comfortable with this? So I can do it to every bit, that is coming in. I can compute its G and P properties in parallel, right? All 32 of them. And what is GP signal, right? That box I showed you in the previous slide. I should have probably colored it in the same color over there also. What was the goal of GP? That we were getting some signal from the high side, some signal from the low side, and combining it to produce the G and P signal again. But we only do it to adjacent things. So that numbering here is showing, I can't read it that far. Okay. So suppose this higher order stuff is from I to J. Then the lower order stuff must be from J minus 1 to 0 or K or something, K. J better be between K and I. All right, so if you have this, I have already given you the algebra for it, how to combine these signals together. High level thing to remember is, even if you can't remember all the details of this, is given the high level signals for generate and propagate, given the low signals for generate and propagate, I can combine them to compute the generate and propagate signals for the whole composite. Only based on A and B. No, carry-ins have been used yet. But sooner or later we have to generate carries, right? That's the goal. And then you see that if I take this propagate from Pij, that box that is sitting over there, what is it waiting for? The higher order bits. What carry they are waiting for? Carry coming from the lower side, right? That enters it. So that's why it's saying that if you know the propagation from I to J, please tell me what is the carry going into J. And that will be Cj minus 1 over here. So if you know that, then I can generate the carry for J. So essentially what I have done is, I have suddenly propagated the carry from the jth spot to the ith spot. Okay, that's the whole idea behind it, by doing these propagates, and now you can actually see it over there. Can everybody compute these green boxes? So far so good? Now I'm going to introduce GP boxes. Do these GP boxes make sense? I'm just taking neighbors and combining them together. I have already given you the formula for combining them together. Once you combine it, you get signals coming out of them. Propagate and generate signals. What do you think is the next step? Combine them again. You keep combining the neighbors, right? So what is the beauty of this last GP?
It can take the first carry to determine.
It can take the carry in from the least significant part and propagate it all the way to the output of the highest part. That's very clever, right? Because we left out the carry signal from this. We just studied the generate and the propagate properties of these circuits and kept combining them recursively, right? And by the time you look at this, you should be very good in figuring out how many delays are there in generating these signals. Anytime you see a picture like this, the safe answer is?
Log n.
Log n, because whenever it goes like this, must be log n, leave me alone, right? Something like that. Indeed, it is log n. We started from 32 to 16 to 8, 4 to 1. Much, much better than 32 chain, right? But we are not home yet. All we have done is we have computed the generate and propagate signals, okay, in order of log n time. All right, so that's the depth of this circuit. Now comes the next part, generating the carries, real carries, because remember, our full adders are waiting. We have a row of full adders. We have to feed all these signals into it, but we haven't got the carries yet. All we have got is the propagate and generate signals. Okay. Does this make sense? Yes, because this one propagated from all the way, right? How about this one? Can you see if you just read the numbers on there? So the first one, the second one, the fourth one, and the eighth one, they're all propagating signals coming from C in. They will all be produced in log n time. What about the other carries? And please understand what happened here. In order to produce, let's just focus on C5. In order to produce C5, if you look at the GP, its index were 5, 4. So I need the output of the fourth carry in, which was here. I'm showing it here. Okay. In order to do this one, I needed the output of this one to produce C5. And you see a row, and then you will see another row. What does this structure look like? All the carries are now produced in another log n time. So it took me log n time to produce, propagate and generate signals, another log n time to produce carry signals. So that is 2 log n times, which in order of notation is still log n. We don't care about constants. In reality we do, but you know, for discussion it's still log n, but it's twice as long, twice the log. Does everybody remember what was the goal? We could do the additions all in parallel, but we could not generate the carries. So now I've given you this whole complex circuit on top, which can generate all the carries in log n time. All I have to do is connect them together, right? So these carry bits will feed the row of full adders to produce the sum bits. Yep.
So all the full adders, regardless if they produce the carry bits, you just kind of ignore them because you already produced the carry bits?
Sorry, say that again?
So like a full adder job, right? Like,
Yeah, but I did not do that here.
so you don't even need it.
That's right. You don't need that. So all that will get simplified actually in your circuit. That's why it's very hard to guess exactly how many gates are involved in this. Okay, so there are many different ways of connecting these carry-look-ahead adders, but the idea is same. You are always trying to capture something about generate and propagate, right? And we have seen the Brent Kung adder, and there are other ones, Kogi Stone adder, and they all try to improve, you know, so it takes less hardware, but they all have log n property. We can't do it better than log n over there. The reason why you should try to understand this technique is it's not just for adders. Any associative operator you have, binary associative operator, this idea will work over there. But this is the slide I want you to focus on. So Brian Wheatman ran all these codes yesterday to produce this result. So let's first focus on the ripple carry adder, right? And you know, in synthesis, you can optimize for time or you can optimize for area. You can use standard gate library or you can use extended gate library. So for example, extended gate library may include an exclusive OR. Standard gate library may not include an exclusive OR. And what do you learn by reading this top thing over here, right? So we were optimizing for time, 4 and 30 gates. The area actually taken is 295. And the delay is 742. And as we go this way, if we use fancier gates, we can drop down the area from 295 to 180. If we optimize for space, then we can, you know, drop it down a little bit more. And this is roughly the timing, not a huge difference in propagation delay. This is your basic ripple carry adder, and the time is of the order of 700 picoseconds in this. All right. Now focus on this recursive carry-select adder which I showed you, and what do you see immediately? If you just stick to basic gates here, humongous number of gates, area 727, regardless of how I do it, right? This area line is definitely higher than the area line for ripple carry adder, which is what we expected. We were taking extra hardware, but we just couldn't quantify how much. This is giving you some idea of how much extra hardware is there, right? But this is the good news. Why we were doing all this? Because we wanted to reduce the delay through the adder. Did it drop? It dropped from roughly 700 to the order of 225. That's a pretty dramatic improvement, right? So all these tricks are paying off. We have dramatically cut down the delay through this adder. And this fancy one, the Carry-Lookahead adder that we showed you later on, is even better because it takes the delay in this is, these numbers are wrong. So which one is wrong in here?
The extended gates.
Okay, this one is wrong. So just copy those numbers, right? So it should be 167 over here. And gates 530, and this thing becomes 483. So please notice, if you compare this line, I mean, we can compare anything. Let's just compare this stuff over here. Definitely faster, and definitely takes more area. What I take away from this is, by doubling the area, right, you can reduce the delay significantly, much better than half it. Do you get the point, right? That algorithm mattered in this, you know. And summary here very quickly: choosing the right algorithm is crucial for whatever you're trying to do, right? Though when you just want to get going and you're designing a complex circuit, choose the simplest one. But write your programs in such a way so that we can take it out and put in a new, better algorithm. And the last point is, carry-lookahead adders perform order of n addition with some area cost. The technique can be used to optimize a broad class of circuits. Please study this, right? If we haven't asked you to implement it yet in the lab, you will definitely need it for the project. So any effort you spend in trying to understand this will not be wasted. Thank you.